So the topic of today is going to be playing with system calls in C#. Now, this is a very specific topic and a very specific methodology to bypass certain EDR defenses. What I mean to say is, well, there are many different techniques and many different techniques that EDRs use to block red teaming techniques. So this one will focus specifically on the syscalls. Now, let's get right into it. Thanks, Tomer. Okay, so who am I? My name is Milan Charniak. I am a red teamer at C-Links. Okay, I do all sorts of stuff from various penetration tests, red teams, etc. I am going to be the presenter today. So we'll get right into it, I guess. So this topic is like really sort of advanced, and you should have some programming experience. I will try to make it very clear though, and it's not a must, as the theory side is quite easy. So you don't really need to understand everything, but you must understand the idea. Okay, so I'll explain like what EDRs actually do to find malware, and I will show exactly what we can do to bypass it, at least partially, as there are many sub-techniques and nothing really is one technique. There is no one technique that like beats all. There's no cheat, like a cheat technique that you just can't stop. I mean, there are, but they're not as easy and plain as it may seem. Okay, so let's get into it. Okay, what are we going to talk about? So we're going to talk about how actually Windows operates, like from application to the kernel to the CPU instructions, which end up on the disk, and various processes. We'll talk about what is usual end hooking, which is the technique that EDRs actually use to try and caught malware, malicious actors, red teamers, like anything. We'll talk about what are syscalls, how can we use them to evade the said EDRs. Said EDR hooking, I must emphasize, since, well, there, and I'll touch it, but there are, again, additional stuff that must be taken into account, but we'll focus on this specific technique today. We talk about how can we convert this said mysterious Win API that I actually haven't explained what it is yet into a syscall, and we'll show some code. So let's move. So the Win API. Okay, on the most basic level, there is something like we all know what it is. It's called operating system, and as the name suggests, operating system is, well, operating the hardware, like your computer, your RAM, your keyboard talk to the OS, your disk, like everything is operated by Microsoft Windows, unless you run some other OS, but this is not the technique. Now, 1 second, I would like to see some. Okay, sorry, let's continue. So on the most fundamental level, if I write a program, and let's say I want to create a file like on the disk, like what is a file? A file is actually a bunch of bits on the disk, and, well, the disk is physically changed. Like imagine you have a disk and it has like 100 slots, and your file takes like 5 slots, and your file is 10010, like that's it. So you actually need to go to the disk, pick up 5 places out of 100 and change them to like 10010. That's your file. Now that's actual mechanical function or electronic. It's actually changed and written to the disk. Now who does that? Well, the CPU. How does it do it? Well, you need to tell it to go to the disk and actually change this 0 to 1 or 1 to 0, because it could have been 1 before. Like it's either 1 or 0, unless it's a qubit, but that's a whole different level. Regardless, so we have file. Now I am, as a programmer, I would like to create this file. How do I tell Windows to, well, write that file on the disk? This is what's called API, application interface. So I can actually take this application interface. There's application interface for like creating a file, like showing a window, or maybe like opening a process, like etc. Like everything in Windows is an API. So this way a programmer can talk to the operating system and like do its magic, like actually influence the hardware. So let's talk at this little graph. So we will have an application and okay, all these Win APIs, they are stored in libraries. Okay, so this is just the way it was made. It has its legacy meaning, but you have something that's called, for example, kernel 32. That's just a big library of APIs. And you have NTDLL. Okay, this is a file and this is a file. These are files that Microsoft supplies with every operating system. They are more or less, they're changed between versions, but they do the same thing. Like if you want to call create file, you will need to go to this file, find the exact API. Now, I'm an application, I call create file. To create file, I need to import something that's called kernel 32 DLL. As we've said, like I need to tell my program, hey, if you want to create a file, you need to call this DLL because the code is in there. So what's happening behind the scenes is we call the Win API. Okay, in the kernel 32, we use this code. This code actually moves on to a next DLL. Okay, like this DLL calls another DLL. Like that's how Windows is built. Like for whatever reason they chose it. Once again, legacy and stuff. Like it's since Windows 98 or 95, so stuff moves. Anyway, so you call kernel 32 and it calls NTDLL, and NTDLL does something very interesting. Like NTDLL is a file. Like we have it, we can open it, we can call it directly. We don't even need kernel 32. We can just go to NTDLL by ourselves. But what NTDLL does, it's not really a complicated file. It has like a few lines of code for every API. NTDLL actually has all the APIs, or most of them, that Windows allows a programmer to use. So if you call like create file, like write a file in kernel 32, kernel 32 knows to invoke a very specific API inside NTDLL that represents create file. Like you can say there's a double API. You can have you can use the create file in kernel 32, and you can use create, which uses NTDLL, or you can actually go to NTDLL yourself and use it as a library and say, okay, I want you to create the file. Okay, that's how it's built. Now, what NTDLL does, it's actually a very simple function. It takes your parameters. Now, every Win API has parameters, like most of them are. Like if you want to create a file, you need to say what's the name of your file. Now that's first parameter. You want to tell them like what type of file are you putting? Like is it media? Is it what is it? Like that's another parameter. What NTDLL does, it does pretty much nothing. It just moves all of your parameters to the kernel. What is the kernel? You're asking? Okay, there is a certain distinction in Windows. Now, every application that's running on Windows is running inside what's called user space. Okay, unless it's a kernel module, but that's in a second. So when I use an application, it runs in user space. When I use like anything pretty much, like if I open my browser, if I use my file explorer, if I installed like a Zoom, it runs in user space. In user space, all the applications share memory. Okay, now I'm not gonna go too much into RAM, as I believe everyone here knows what it is, but every application has its virtual memory. Like every application in the computer believes it has all the RAM. Like if you have 32 gigabit RAM on your PC, like Zoom thinks it has 32 gigabits of RAM. and so is Firefox, and so is Brave and Chrome and whatever. Now, the OS actually what it does, it does a mapping, like every virtual space, like let's say you're using Zoom, like Zoom has like place 0 in memory and like the final space, like FFFFF or something. So there is another application that also has 00 and FFFFF. Now, these are virtual. In fact, like the 00 of one application goes to an actual real memory address, and the 00 of the second application goes to another real physical address. So in user space, all the applications are separated. But in kernel space, all the kernel drivers, which are actually the piece of software that like talks to your keyboard, like actually moves bits in the CPU, now they all share the same memory space. Okay, they are all aware of each other. They all can affect each other. And unlike the user applications, which are separated, they can talk, and we'll talk about how can they talk, but that's a different story. In the kernel space, everyone is together. And what NTDLL does is actually talk to the kernel space. Now, what exactly NTDLL does, I'll just show it in a moment. It has, okay, let's talk about CPU. CPU is basically just instructions, okay? Like CPU, like the most basic version has like 8 instructions. In assembly, like every instruction does something else, and with simplifying it, and I'll simplify it as much as possible, every combination of functions does something else. Now, all code you will ever write, like Python, Java, NIM, Rust, C#, whatever, in the end of the day, they all end up looking like this. Like everything in the end looks like this. These are opcodes. What is an opcode? An opcode is the actual name of the command to the CPU. So if I write something, the CPU sees that. I can write it in Python, I can write it in C, I can write it in NIM, whatever. They all, in the end, to the CPU looks the same. The CPU doesn't care, okay? It doesn't understand languages. It understands CPU instructions. So what is kernel 32 actually does, I mean NTDLL, it uses these 4 lines. Now, this is a CPU instruction, this is a CPU instruction, this is a CPU instruction, and this is a CPU instruction. Now, a regular program has like thousands, tens of thousands, like hundreds of thousands of lines. NTDLL does not. Its whole job is to communicate between userland and kernel space. Okay, so you write an application, you create a file, you import kernel 32 DLL, you invoke the Win API. Kernel 32 just moves the code inside kernel 32, just goes to NTDLL with all your special parameters, etc., and does syscode, which is what I showed you right now. Does this, okay, and moves it into the kernel. And here's where all the magic happens. Okay, cool. Now let's talk what EDR do. Okay, let's talk about like the most basic malware. Like, what does a malware even do? Okay. Now, again, I'll presume most of you guys have some good background. Some of you like have insane backgrounds. Some of you like, okay, I understand what you're talking about. So I'll talk to like all levels, and I'll try to be as clear as possible. But let's say you have a malware. Let's say that creates a malicious file like that runs automatically when you boot the computer, like something very simple. Okay. Now, let's say in this example, we're talking actually about injections. So let's talk about injection really for one little second. What is injection? Okay, so you have these memory opcodes, okay, these instructions to the CPU. What a malware can do, okay, let's say you open a malicious file and you close it. Like the malware is dead, right? No, it's not. It's still running. Like, where is it running? Well, it can run inside your Chrome browser. What? How? You didn't open it in Chrome. What did you do? Well, the malware actually creates a copy of itself or copy of another malware and injects it into another process. Okay. How do you inject stuff into processes? Win APIs. again, like the OS is in the end is Win APIs. There's like no magic here. So a malware, what it will do, it will use 4 specific Win APIs, and I'll actually show you an injection, like how it looks like. I hope you're seeing that. Let's see. Let's look at this for a moment. Now let's make it like really, really simple. Like there are like 4 functions in here. Okay, I know it's escalating really quickly, so please bear with me. So first of all, let's say I'm a malware and I want to inject myself into Explorer. What's an Explorer? Like this is Explorer. Okay, this window here is an Explorer. Now, what malware does, it says, okay, I want to inject myself into the Explorers. Then when someone kills me, like if the EGR kills my original process, I'm still running inside Explorer. Okay, how do I do that? So first of all, I get the Explorer, I get its process ID. Okay, every process has an ID. That's how you refer to them. You don't say Mr. Explorer because you can have 1,000 Explorers. You say ID number like, I don't know, 8885. Now you say, okay, so I have this Explorer. Now Win API presents us with a special function. It's called open process. So when we give this function, this Win API, and when I say function, I mean Win API. When we give Win API the process ID, if certain circumstances happen, like permissions, etc., we receive something that's called a handle. Now, a handle is a C# project which you can use to refer to address space in another or your own process. So you get a handle, like just like it means a handle to something, to a process. At this case, I'm getting a handle to something that's called Explorer. So I'm now having a handle to Explorer. Cool, what can I do? Well, Explorer has its own virtual memory, as I've said before. Let's allocate special memory inside Explorer, okay, and inject our own malicious opcodes inside this process, inside this memory. Okay, so enter virtual alloc. Okay, virtual alloc is another Win API. So we open a process, we receive its handle, int ptr h process is the handle, and we pass this handle to virtual alloc. And we tell virtual alloc, look, please allocate us this and this memory inside this process that we would like to use. Give us permissions, okay, and let us write into it. So we now receive some space in some process. Okay, what do we do with it? Well, we will write down our own instructions. Now, these are our instructions. In this case, yes, they have been generated with the most basic and pretty much obvious C2 framework out there with Metasploit. Like it's the most basic thing ever. You just do this. You just say like, I would like to have like a shellcode that will like do a reverse shell, which is like in this port. And MSF Venom, like the easiest one out there. Yes, not very recommended for day-to-day use, but for POCs, it's great. And it just gives you a shellcode. Now, what this shellcode does, it actually returns some traffic to this address on this port. And whoever receives this traffic can then run code on the inside the process that invoked this. Okay, so that's what we want to inject. Cool. So we have something that we want to inject inside a memory space. So let's do this. Write process memory does exactly that. It takes our shellcode and writes it into the remote process. Okay, we specify where to write it, the address which we received from virtual alloc. What do we want to write? How much size is it going to be? And there's a special parameter which I will talk about later. Okay, so we have Explorer and we have special place in memory, and Explorer now has it inside. It has our shellcode, but it will not execute it because we did not tell it to. So how do we execute? Okay, there are processes in Windows and there are threads. If we say a process, like if you open like Explorer, it's a process. Now it has many threads that do many things. That's how it works. There's no one single thread. But what is a thread really? Well, a thread is just a bunch of opcodes, because in the end of the day, the CPU doesn't care about the language. It doesn't care about processes. It doesn't care about anything. All it cares about is this. So we just create a new thread. We use additional Win API and tell Explorer, hey, please run a new thread on this address. Now, well, this is what the Explorer will do. It will go to this address, which is exactly the start of this shellcode, and it will start running. It will go one opcode at a time. And when it will finish, we will receive a shell. Okay, that's injection. So what EDR can do about it? Like what's all about it? Well, when we use, like, let's say, create remote thread, okay, which is this one. Like, I finished, I've written my shellcode, I want to invoke it. When we use create remote thread, we need to import a specific DLL. As I've said, all Win APIs reside in DLLs. So in our case, create remote thread resides in kernel 32. Now that's a DLL that has like very, like, probably most of the important APIs in Windows. But we invoke kernel 32. What the EDR does, when we invoke this kernel 32, when we do import of it, it actually changes it. Okay, the EDR just involves itself and edits the functions, the Win APIs inside kernel 32. What they do is, when I create a remote thread and I use the DLL that was tampered by the EDR, I think I'm calling the create remote thread, but in fact is I'm calling a special jump instructions from the EDR. The EDR receives all my parameters because because my software thinks it's a create remote thread, and the EDR gets the parameters, inspects them, and says, okay, so you want to create remote thread on Explorer. Like, that's nice. What are you actually invoking in there? So it will read the shellcode, it can read the parameters, it does some logic. It can say, okay, so you want to write into this address, right? You want to invoke a remote thread, I mean, in this address, right? Let's see what's in there. EDR opens it, like, okay, what does this shellcode does? Wait, that's like meta operator. So it blocks you. It says, no, I'm not, that's malicious. It blocks you out, kills your process, and alerts the user. Now, if, let's say, I was invoking here something like stupid, like, I don't know, a message box, or like create a new file, like a new TXT file, which is a harmless, the EDR would say, okay, whatever. Like, and it moves me to the real function. Okay. So you can call it a man in the middle EDR stack. So that's what's called userland API hooking. Okay, very simple concept. So what's a syscall? Basically, as I've said, you have an application which invokes kernel 32, which goes to NTDLL, which then goes to the kernel. How about we just go to the kernel and skip everyone else? That's a syscall. Okay, we just don't care. Nope, you listen, you tampered without DLL. Yeah, that's nice. We don't care. We just talk to the kernel. That's the whole technique. Okay, and it allows us to bypass userland hooking. Now, there are lots of different ways EDR can spot us, like binary strings. Like, if my malware even has this inside it, like if I compile it, the exit that has it inside will be scanned, and the EDR will say, like, why there is a meta pattern inside your exit, and it will delete me, alert the user, etc. So there are various things you need to include before you actually run your malware. So how do you deal with, let's say, shellcode identification? Well, obfuscation, but that's a different story for another lecture, etc. So here we're talking about the syscalls, like the concept of a syscall, like how do you actually use it? And let's get into it then, right? Right. So what is the procedure of generating a syscall in C#? Now, before I get to it, the original syscall technique, sys whispers, was made for C and C CPP. I've seen variations in min nowadays. Like you can implement it in any language, but really it started as more of a C type thing, low level. And in order for it to work in C#, we need to do some kung fu, okay, like C# fu, because C# is a very high level language. It's not most high level language, but it's not low level, that's for sure. But we'll see how we can do it. So what is the actual flow of creating a syscall? Now, here's where it's getting a bit complicated, but I'll really try to make it like super easy to understand. So I'll just keep the flow. Maybe I'll try. Let's start with the flow and then see what happens. So I want to invoke a syscall, and I don't want to use NTDLL, okay? Because usually the hooks are either in the kernel or inside the NTDLL. So like, okay, like how do I not touch them? Well, let's create our own NTDLL implementation. Like I'm creating my own implementation of the NT-open process call. Okay, so when a regular process does this, like open process, when a regular process does this, I give him a PID, few parameters, like what the permissions I want on this handle. In the end of the day, it goes to the NTDLL and does this. So let's do this ourselves. Like let's implement these CPU instructions and give them to the CPU instead of the CPU going to the NTDLL by itself and reading exactly the same thing out of there, except that this time it will also pass the EDR. So let's create this. Okay, how do we create shellcode inside C#? Well, we create an array. Okay, now a byte array. It's an array of bytes. Like yeah. So we create a syscall. Okay, we create this shellcode. Now we just have a variable. Okay, what next? How do we invoke it? Now here comes some interesting concepts in C#, because in the end of the day, C# can't really talk to an API by itself. What do I mean? What I mean is Win APIs are legacy. Like NTDLL, like kernel 32, they don't talk C#, they talk C. Okay, when you want to invoke I think I have here like this little, like NT-open process. Like, look here, like this is straight from Microsoft. Like this is how you use NT-open process. Now these are C types. Okay, these are not C# types. But C# will do this. I'll get to it. But at the end of the day, C# must talk C. Okay, because when we invoke a syscall, the syscall will not accept our C# variables. No, it won't. It just doesn't know what it is. It expects C-type variables because, once again, it's legacy. It's been there for like 30 years. Okay, way before C# was invented, way before anything was invented, like from higher level languages. In the end, Python, if you invoke Win API, behind the scenes, it converts all you write to it into C types and then goes to the Win API. Okay, so we must understand this first. So when we talk about C#, we need to understand something that's called interop. So how actually C# can like create files, like open processes. How does it do that then? If it supposedly is not C, how can it do it? Well, it's called interop. Now interop, okay, is this. Okay, now let's take open process once again. Let's talk about open process. Yes, so this is open process. These few lines, like we import the kernel 32 DLL, like just like in C. Okay, and we pass. Now we define here the function, the actual Win API that we invoke down the line. Like we invoke it here. Like this function is defined here. So what does this function expect? It expects unsigned integer. It accepts a Boolean, like true, false. Unsigned integer is like number. And process access is actually numbers, like 1 is write, 2 is read, like 3 is write and read, etc. And the process ID, which is a number, it's integer. So it expects an int, a Boolean, and an unsigned int. Okay, okay. So as per Microsoft documentation, let's see, I've talked about open process, right? So this, wait a second. Open process, client ID. See a moment. Oh, that's anti-open process. Okay, yeah, okay. What we're seeing here is the kernel 32. As I've said, like anti-DLL has implementations of all the functions. It's just there to talk to the system. Okay, just there to move your API request to the kernel. So the open process, like the regular open process function, as per Microsoft, we can just look at here. As Microsoft documentation is this. Okay, it accepts a D word, a bool, and another D word. Now, as you remember, here was unsigned int in C#, and here was an int. Now, what happens is, well, most of the many C# types can be converted into C types. Like if you write int inside C#, that's int in C2. And if C# passes that to a C function to win API, it still passes a number. So there is some correlations, like some overlap between the languages. But here, there is some sharp foo. So let's see it. Not all C types are actually that easy. Like not all of them are int and etc. But we'll get to it. Let's talk about this for a second. So here, instead of D word, I'm using unsigned int. And here I use int. Now, how do I know what to put in here in the first place? Like, how did you know? Like, very simple. Many programmers before us already did this. And there's something which is called pinvoke, which is a great source for this, pinvoke.net. And if we look here for open process, they will tell you, okay, this is the anti-DLL version, the one lower. We want kernel 32 open process. Let's see how it looks. And programmers before us already did that. Okay, we can just copy this into our code. And now we can use the Win API called open process. Okay, no magic here. So there are various functions in here and there are more sources. And if you're stuck, like you just can't just move it, you can do it manually too. Like in the end of the day, all the data types return like there isn't much new at the end of the day. There are special structs and I'll touch them in a moment, but we'll get to it. Okay, let's just stay simple for now. So here's open process. So we invoke it. Okay, in C#, this is a Win API. This is not a native C# function. This is not like, say, process get process by name, which is a C# function, yes? No, this is an actual Win API, the lowest level there is, well, almost. So this is how you convert C# into C. Okay, cool. That's called interop. So I have interop. What about it? Like, what do I do with it? Well, except the fact that you can call Win APIs as normal, like I did here, like I used virtual alloc and write process memory and create remote thread, create remote thread. As you can see, all of them are interop because they are not really, they do not exist in C# as themselves. So here we have the function, they do their stuff. But if I want to talk to anti-DLL, I need to talk to it as if I'm talking to C, because anti-DLL in the end of the day understands C. It doesn't understand C#. So we can elevate interop to communicate with them, to imitate actually anti-DLL. Okay, so this is interop. Okay, well, how does it tie together? We'll get to it. Now, Here's a more complicated example. So you have open process, right? Yes, I do. But we are actually faking anti-DLL open process. And we're not faking anti-open process. We're not faking open process. Okay, we're not trying to overwrite kernel 32. We want, which will move it to anti-DLL. No, we want to go directly to the kernel. So we need to go directly as if we've passed through anti-DLL. Now, as I've said, every anti-DLL function has its own implementation. Like, let's look at open process, anti-open process. This is an API that is imported from anti-DLL, and it accepts a little different parameters. Like it accepts a handle, like access mask. Let's put them one next to the other, actually. Let's like do this. Like, sorry if this is a little bit messy. Let's make it like this. So we can see that these functions are a little bit different, really. Like it has p-handle, like no d words, like 4 parameters. Here's our 3 parameters. So there is a difference. Okay, so we'll have to implement anti-open process rather than open process if you want to talk to the kernel. Okay, so how do we do it? Invoke as one option. Yes, large it. Let's say anti-open process. Is it here? It is not. Is it here? Most probably yes. Hello, anti-open process. This is the implementation. Now, take heed. Sometimes this implementation isn't actually working, and sometimes it's worth to actually go to MSDN and do it yourself. But most of the time it does work. And you can actually go to GitHub and find implementations of people. People already wrote many syscalls in C#. Like it's not something new. It's a technique from like, I believe 3 years ago when I think Andrew Special was the first one. No, Dumpert, I think. It was Dumpert who actually like mainstreamed this technique. It was implemented in C. But since then, many different implementations have been done. Programmers use anti-DLL too. Sometimes they aren't using the kernel 32 DLL. They actually go to the anti-DLL by themselves. Okay, but they're invoking it. They're not creating their own version. They just talk to the high-level anti-DLL. But we want to fake it. So if you want to fake it, we want to pass. Now, remember that anti-DLL, in the end of the day, this is anti-DLL. Now, these instructions, they accept some parameters. Like these are commands in the CPU. But before these commands are invoked, special parameters are passed to them. Which parameters? Well, these parameters, because it's a function. It's just a proxy. It just moves it to the kernel. So we need to give it a proper anti-open process function. So we need to create one. How do we do that? So this, okay, and fear not, I will explain. This is the Win API version of the most basic injection, as I have explained before. Like this is the most basic one. Like there is nothing like less than this. And that's on purpose because we want to be, this is not what we're talking about. We're talking about syscalls. Now here, let's see, is the exact same version. You should not be here. Implemented with syscalls. Okay, like these are the same functions, but with syscalls. Okay, and I'll take one function, anti-open process. We'll just roll with it. We'll see how you define one. And the nice thing about it is once you get one, you get them all. Like if you can define like one syscall by yourself, it's not that hard to transfer that knowledge and that skill to all the other functions. Okay, because in the end of the day, they all look the same. Okay, So let's do this like this. Let's go with the code really. So we have a function. Okay, now there's lots of comments in here. Maybe some cleaning will help. So we want to define a new function called anti-open process, which will move our parameters into the syscall like the original one does. So we need to create our own anti-open process and pass it to our CPU instructions, like it was in nature, if you can say nature, like Bill Gates intended. Now, let's see. Delegates not yet. Defining data types. Okay, look, open process is easy, like the basic open process, like not you, like this one. Nope, not this one. I mean this one. This open process is easy. Now, the anti-open process is a bit trickier. Now, as I've said, int and dword and uint, like uint and int in C# can be invoked instead of dword in C. But C has some tricky data types, like structs. Okay, now what's a struct? A struct is a variable. Now just show one as an example. It's a, this is a struct. Okay, no, this is an enum. One moment. Struct, const. I'll explain what all of these do, but in a moment. Okay, we're using an enum here, which is okay, but I want to talk about structs. Okay, let's talk about struct. So you have classes, right, in C#, and you have structs. Now, a struct in C# is like type in C. What is the type? Like you have an integer, right? Like int saves like number from one to like, I don't know, like billions. Okay, but what if I want to have my own variable, like which will represent like a person, like it has a name, it has like a family name, like age and gender, like 4 parameters, and I want to have them as a struct, as a primitive, not a primitive, as a type. Okay, yes, C does that. Microsoft has their own built-in types that they are using. Once again, that's how people choose to do that. So we just roll with it. It's like we can, this is how it is defined. So like, let's talk about open object attributes, like this struct. Like this, if you look here, and our anti-open process, okay, which we try to find, is return is of type, like we define here a variable of type anti-status, okay, and we put inside it the output of anti-open process. Like, okay, like what is anti-status? Anti-status is a struct or an enum in our case. Enums are they're not structs; they are just verbalization of words. Like if I want to say like anti-status, like dot success. If a program returns me that, what it actually means, it means zeros. It means anti-status dot success. But I presume most of you do know some programming, or most of you like know a lot of programming, and so I don't really go deep into that. But these types from C, like let's look at anti-status for a moment. Like, what the hell is it? It comes inside the library. I don't remember which in C, but in C# you need to create it by yourself, because when APIs, they expect anti-status. Like, look at all of this. This is horrible, yes, but it's not that horrible because someone already did that job for us. So you can shamelessly copy it, yes, like here, like shamelessly. So you create an object called anti-status. This is an object, okay, and you invoke it right here. And you invoke it right here. Now there's another object, process handle. Now process handle is actually a native object to C#, so it's like in PTR, so that's okay. We don't need to do some crazy kung fu here. ref, obge, and client ID, as per Microsoft documentation, which is not here, into open process. Let's see what Microsoft expects us to do. And I'm putting a special emphasis on this because this is actually the hardest part of all of this technical. If like once we pass this, like it's peanuts. Like this is the easier part. So anti open process, as per Microsoft documentation, like receives a handle, an access mask, which is there's no such thing as access mask in C#. It's a struct. It's someone defined something called access mask, and it has project attributes. Like again, what the hell is project attributes? And the client ID. What the hell is this? If you go a bit lower, here's an access mask and here's object attributes. Okay, what is an object attribute? You ask. This thing, struct. Okay, now struct in C++ is similar to struct in C#. So if we define this in C#, we're good to go. Now, again, ulong probably will be int or uint, and handle is ptr. Like I said, pvoid is a void pointer, I think. Yes, it's actually a void pointer, which we can define by ourselves. It's a pointer in the end of the day. And there is a nice table like for all the converts, which can be found online. And you don't really need to do that, but you must understand the concept. Okay, at the end of the day, somebody already written this for you. But we need to understand what we are doing. So we have poke handle. Let's go to the actual definition. Now here in the open process, as I have implemented it, it receives a process handle, which is a type int ptr. It receives an access mask, which is actually an unsigned int. It's a number, guys, nothing else. Ref. Now, okay, let's talk a little bit about managed and unmanaged code in a bit, and I'll get it. So it receives object attributes, which is a struct. This is object attributes. This program is split into 3 files, actually. There are 2 classes in the main program. Like this is the main program, like nothing to see here, like just invokes. And this is the native. Okay, here we defined all the structs, okay, that we use later, like all of these scales. We can clean it up a little bit, like that's anti-status, that's object attributes, that's client ID. We saw it like a minute ago. That's actually just 2 lines. It's like nothing. These are public constants which are used. They actually aren't used. I'm actually not using them in this code, so please ignore them. You can just, by the way, you can use just the number. Like instead of invoking this, if you define like a constant, you don't need to use this. You can just write this, and the code will get you. I think that's exactly what I did in the native code. But we're getting a little bit off track in here. Like access mask, I can pass like an object, which means 001F0FFF. I can just pass the number left. That will work too. And just more ordered that way. So in the native part, here, you keep confusing me, so go away. And this part, we can see like all the structs we've defined, like allocation protect. We'll use it in another function. We'll actually use it here. I'll get to it. So these are types, these are structs, and in interop. So they're just a little bit more complicated, but in the end of the day, here's an int and here's an allocation protect. Like same thing. Like enum and structs. Sometimes you will use a struct. Sometimes you will use an enum. When will you use an enum? When you want to do something like this, like instead of writing here like this thing, you will write something nice like access mask allow write and read, instead of this thing which is irreadable to someone who didn't like read it the doc or not read it in the first place. So we define a function that looks like the original anti-DLL. We wrote a function. Okay, let's be more friendly. So we create a wrapper function. We have also created a syscall number. Like we created actually a binary array that holds our shellcode. And we have a wrapper function. Okay, what do we actually want to do with that? Let's talk a little bit about the theory. What we want to do, I'll try to draw it. Like, we want to create a function which is like NTDLL. We want to create it ourselves and pass it, okay, to the syscall. That's it. Fake this, and it will do all the rest. It moved to the kernel. So we already have the syscall. Like, this is the byte array. Byte array. I'm not a great painter, but byte R. So this is the main work. Now we know that this function must use C types because it's in it's actually created by it's actually imitating a legacy Win API, and this Win API uses only C structs. So our C# must have this in C types, because when we move these types to our syscall and it moves it to the kernel, if there are C# types here or something not clear, the kernel will say like, what? Like, say what? Like, what do you want? Like, and it will just crash. So we want it to be precise. Now, how do we define this wrapper function? Like here, and like, let's isolate you really, really clearly. This is a wrapper function, okay? It receives 4 parameters and it passes it to our shellcode. How does it do that? How? Let's see. Let's go. Now, here it looks a little bit convoluted, but there's one, but it will get clearer. There's one more concept that we need to talk about. Like, you want to move here. Now, what is now where is our syscall? In memory. Okay, it's not on disk. Like, the original syscall is written in NTDLL. Our is in memory. So we want to call it, so we want to move these parameters to this memory, and it will do the same. So how do we pass parameters to memory instead of a function in C#? Well, enter delegate. Okay, what a delegate is, like, if I like, I'll tell you the definition, and like, it's basically a delegate is exactly that. You give it a point in memory and it will pass parameters to that point in memory. So if we give it our shellcode location, it will just pass our parameters to this memory space. Like, that's what delegates do. What is their actual use? Well, they use as callback functions, but that's different topic. For our needs, a delegate does just what we need. Okay, so what do we need? So we have a delegate, right? Yes, we do. And let's see. No. Now we have a delegate. Because a function cannot actually access memory by itself. No, it cannot pass its parameters to memory. It must use a delegate that will do that for her. Okay, so that's the flow. And we create a wrapper function which takes our shellcode. You're too fat, you look good. Which takes our shellcode, like syscall, and moves it to our delegate, which then takes the parameters, these parameters, and shows it into the kernel, like via this syscall. That's it. Now, it is exactly the same to all functions. Like, any syscall you will ever do will look something like that. There's nothing else about it. So how do we do that? How does it look actually? And here we define a delegate. Now, this is the same code for all of them. it's a struct, okay? And I will show you an example, like how does it look in the end. But we need to talk about one more thing, like before we get it rolling. Like, how do we give C# an actual place in memory? Like C# is actually based on something called .NET, okay? And also Visual Basic and some other stuff. But the reason why .NET exists is simplification, okay? Instead of writing like 100 lines of code, we can do same thing with 50 lines of code. Like you don't need to manage your memory. You don't need to allocate like variables and then destroy them and make sure like your stack is okay and etc. You don't need to like create memory and manage its permissions. Like no need. Like C#, like the .NET actually does it by itself. So that's the beauty. But if you want to use pointers, C# doesn't know how to work with pointers. Okay, not directly. It has PTRs. Okay, it has references, but the reference in the end of the, okay, let's say it like this. .NET has a garbage collector. Okay, when you have used a certain variable, it is destroyed. Okay, when the garbage collector understands that a certain variable will not be reached by any piece of your code, it is just removed. And once it is removed, all of your variables are compacted together to save space. Now, if I hardcode a pointer in a C# program, and my garbage collector like removes like other like C# objects and then compacts the whole heap, like my pointer now points to like to the same memory, but now there's something else in it. So my pointer breaks, it can't work. Okay, I cannot use it. So what C# does, it has something that's called unsafe. Now, once you declare a piece of code unsafe, that piece of code will not be touched by the garbage collector. It will not be touched by the .NET at all. It's called unmanaged code, okay? .NET is called managed code, and unsafe and C and native APIs are unmanaged code because no one is managing them. Like you're the manager, basically. So you do everything manually. So once you declare the unsafe, and let's make it bigger. Once you declare unsafe, okay, you can work with pointers. Okay. Now, the moment your unsafe code ends, like GC comes back, a garbage collector, and like everything outside of this memory space, like is managed. So you need to be careful. And once again, not to break your pointers. So how do you do that? Let's look here. Now you have your bytes array, which has your shellcode. Okay, this is it. This is it for reminders. And you can create with this piece of magic, actually these two pieces of magic, you generate a pointer to your memory, to this variable. Like this variable is saved in memory, as I've said before, like everything is saved in memory. Now here you create a variable that refers to the address of this bytes array. Now what's an address is? Basically a pointer. A pointer is a variable that holds the value of location of another variable, like this. Like you have this variable that holds this address. Okay, now this address is the actual location of the variable. If you go here, this is the value. If you go here again, this is the value. Now what does that mean? That's actually, if you go here as an address, okay, this is the address, this is the value, it's 10. So this thing holds the address of this 10. That's a point, okay? And that's what we're doing here. We're creating a pointer to this variable. Now we know, now we can reference it, now we can call it, okay? But as I've said, this is an unmanaged code. So if it's unmanaged, you need to manage it. Now you create a shellcode, okay? And you, right here, see, you create a Cisco PTI. You're now in the unsafe zone. We specified it. It's an unsafe zone. And Inside this area, since you now created a new memory, you just take a memory, you need to manage it. Like, what permissions would you like to have on that memory? So to manage permissions on a memory, since the C# won't do this for us, we're now in the safe zone, we use a Win API called virtual protect. Now, virtual protect is what it does. It just specifies what permissions can you have on a specific address. Okay, it's a function used in C like all the time, and C# less. It's a Win API, and we invoke it here to make sure that now our syscall is readable. Okay, and when we can read it, we can send stuff to it. Read it, write it. Okay, page execute, read, write. Okay, so we create now, I'll repeat the process. We take this byte array, put it in memory, create a pointer to that memory, and make sure that that memory is actually readable to us. Okay, so now we have actual syscall in memory. Let's use it. Okay, let's actually use it. So this is how it looks in the end. VS. Once again, focus only on this code. Now, this is the wrapper function I have referred here. Like, this is the function that actually acts as anti-DLL. It receives our parameters. It creates the said shellcode in memory. And what it does, and here is the actual magic. As I've said, delegates receive memory addresses and pass parameters to them. So we take all of this beauty and send it to our delegate with the address of our shellcode. This is it. Like, this is the delegate. Please, this is the memory address. Move all these parameters, which you get here, to that memory address. And the CPU will do its magic. That's it. That's a function. Now, this is anti-open process. If you look here, it's exactly the same for allocated memory. Like, look, the parameters are different, yes? But in the end of the day, shellcode, syscall, memory address, delegate. Let's go here, write virtual memory, same. You create a binary array, syscall, memory address, make sure you can write to it, use a delegate to that memory address. Okay, same. Let's talk one last thing. Let's talk about the actual syscalls. All the syscalls look like this. Like, this is open process, memory thread, virtual memory, allocate virtual memory, write a virtual memory. So what's the difference? Well, this little bit. Every syscall has a number. Okay, like if the CPU sees like C1, it sends it to the relevant parts of the kernel that invoke the create remote thread. Now, if we put here 26, it will go to create a file. No, it's not create a file. That's 55. This will open the process. Okay, so all the syscalls look the same. Like, that's the beauty of it. Now, how do you know which function is which number? Well, you have a specific, let's see, there is a GitHub project. I have referenced here. Yep, here it is. Hello. All the syscalls of all anti-functions. Very easy. Like, let's say, create like thread. Now, create thread is create a thread in your own process. Thread X is create on remote process. Now, if we go all the way here, now this is based on a timeline. Like this, I think it's like Windows 98 or something. This is the latest. This is Windows 10 version 20 something. Yes, like 2004. Like if there's a change, then it will be updated here. Like if you're running your malware like on a like old version of Windows 10, like 1709, now the call might be different. Okay, they change it like every few versions. So you need to keep track. Now you can hard code all the variations in your malware, obviously, but you must take this in notice since it will not work otherwise. So there's that. Very easy. Like let's see, like create remote thread is C1. Okay, create remote thread C1. That's it. That's magic. Okay, so let's talk. Let's look into the program. Delegates, as I've said, you define them too, all the same. Like all the delegates are just imitations of your own original wrapper function. Same syntax. Now, like these three APIs return empty status, which is a Microsoft struct, as I've said, etc. Now let's see, does it actually work? Like, okay, you have, now when I say work, once again, we're talking about a sub technique, and there is, I'll touch to it in a moment, but let's see it in action for a moment. Like you have runner native, okay, like all the regular functions, like this is pure Win API, like no syscalls at all, and you have it compiled like here, runner native, okay. Let's actually build it. Okay, like this is the location, and here we will have our MSF console. Let's load it up. Let's run our handler. Okay, it's a little bit of killing. Cool. Now we have it running. Here's our runner native, Cisco runner native. Run it. Hello, shell. Now that's the regular Win API injection. Okay, what it does, I remind you, it goes to the Explorer, which is this thing and this thing. It just creates a shell. Like it goes here, it opens a handle, it allocates memory, injects this thing, like this is the shellcode, this is the malicious actions inside that process, which is Explorer, and then it creates a remote thread that starts at 0.0 of this thing, and it runs. Okay, and that's how we get the shell. Now this is the regular one. Now this, okay, is our syscalled version. Okay, which uses only syscalls. Okay, for these 4 functions. Let's run it. It is here. Okay. Hello. And this is our shellcode. Let's see. Let's use like 3. No, I am in the shell. Okay. Am I? That's me. Okay. This is it. One final note. There are many projects out there that have already implemented various syscalls. You can absolutely copy them. That's open source. Like, you know how it works. You can be a script kiddie as long as you know what you're doing and you understand the code. You don't actually need to write all of it most of the time, but sometimes you do. Yes, if you want to do something beautiful, but that's a different story. Let's like SharpCall, that is a project from GitHub that has various implementations. That's like, this is the POC, and I need to give a shout out to the actual guy who first introduced this technique, okay? And I'm talking about Jack Haler. This is the guy who actually put the first blog post like a year ago about this technique in C# specifically. So you should really follow him. And there's additional reference, like, okay, how do you detect the syscall? Like, okay, you have syscalls, like, sure, you cannot hook it, but what can you do? Well, there are various ways you can do it. Now, first of all, it's very suspicious if a software, okay, invokes syscalls on the CPU without actually going to the NTDLL. That's like weird. Like you didn't call NTDLL, but you're using syscalls. How can that be? So that's one obvious way to spot it. And that's what EDRs actually started to do as of late. So what do you do with that? Well, instead of creating our own syscall, as we did here, a more advanced technique, and this is out of the scope of this one as it is already complicated enough, is to give our delegate the actual memory address of the function inside NTDLL. Like instead of, like this is the original way, instead of creating our own syscall in memory, we can find via various enumerations the location of the original NTDLL syscall inside the DLL, like its actual memory, like where it is, and just give it here, okay? And in this way, the EDR will see that you're actually invoking the NTDLL, but you aren't, and that's the beauty. One additional way you can do that is actually by like EDR can look at, okay, this binary string, like that looks like a syscall, like so you can obfuscate it. You can do here like gibberish commands, which is an additional way. Like these are more advanced topics, but you must understand this to do this, okay, to actually bypass EDR. Okay, now once again, it will remove some scoring from VirusToggler, but you need to obfuscate your executables. Like there's nothing else. Like you need to put anti-debugging, you need to obfuscate your shellcodes, you need to do some decoys, like sandbox detection, like etc. These are additional techniques. But the syscall, in the end of the day, is there. We just talk to the kernel directly, okay, without invoking the EDR API. So that's about it. Oh, it's already 6:15. Time flies. All right. So I've been Milan, and thank you very much, guys. Hope you have a great week.